Electron configurations in the periodic table. In chemistry, we refer a lot to something that we call valence electrons. Valence electrons. These are the electrons that are in the outermost principal shell, which would be the principal shell with the highest principal quantum number n. So those are the whole numbers, 1, 2, 3, 4. So if it's 4s, that's the fourth level, right? So those in the highest principal shell are the farthest away from the nucleus. And they are very important because those are the electrons that interact with other atoms and get involved in chemical bonding. Any of the electrons that are not in that highest or outermost shell are called core electrons because they're on the inside. So this would be a little bit like the apple core, and this is more like the skin, the part on the outside that we're looking at. So if we look at an electron configuration for silicon, 1s2, 2s2, 2p6, 3s2, 3p2, we're looking at these large whole numbers here. 1, 2, 2, 3, 3. 3 is the largest number, right? So 3 is the highest principal quantum number. All of the valence electrons are in the third level. There's 2 in the s subshell and there's 2 in the p subshell. So these are the valence electrons, and everything else are the core electrons. Let's write an electron configuration for chlorine and identify the valence electrons and core electrons. How many electrons does chlorine have?
17.
It has 17. So the electron configuration, 1s2, 2s2, 2p6, we're up to 10, 3s2, there's 12, we need 5 more, 3p5. What's the highest principal quantum number? Is 3. So these 2 subshells are in the third level. And so we've got 2 plus 5, we've got 7 valence electrons. And these guys are core electrons, and so there's 10 core electrons. Any questions? This shows us where this concept of valence electron comes from. We can actually figure out the number of valence electrons just by looking at the periodic table. Let's look at selenium. Selenium's a little more complicated because it's got some 3d electrons in there as well. But still, the highest principal quantum number is 4. And so we're not going to count these guys, even though they come between 4s2 and 4p4. That's 3. It's the principal quantum number that matters. So there's 2 here and 4 there. That's got 6. The d electrons are core electrons. And so all the rest of these in the blue are core electrons. Here's a piece of the periodic table. We're showing the last term in the electron configuration. Hydrogen only has one term, so it's also the first term. But all of these guys end in some number S1. This is row 1, row 2, and row 3. 1s1, 1s2, 2s. Start that over again. 1s1, 2s1, and 3s1. All of these guys have one valence electron, and they are in group 1a. Group 2a elements have 2 valence electrons. Their electron configurations end in s2. 2 in the second level, 3 in the third level. Remember, these are called periods. And then this little gap here is that big gap on the periodic table, and we're jumping across to the other side of the main group elements. Group 3a, how many valence electrons do these guys have? We've got 3, right? How about group 5a? How many valence electrons? 2 plus 3 is 5. How about group 7a? 7. In group 8a, now helium Helium is a lot like hydrogen. He's an exception to some things. He only has 2 electrons, so he doesn't have 8 valence electrons, but kind of ignore him. The other noble gases have 8 valence electrons. So this is 2s2, 2p6, 3s2, 3p6. The guy under him, krypton, is 4s2, 4p6. The group number gives us the number of valence electrons for the main group elements. Here's the whole periodic table. All this S, P, and D stuff is hiding in the periodic table. And what is super cool, at least to me, is that the shape of the periodic table was determined to be this way because of repeating properties. It was after the creation of the periodic table that we understood how the electrons were arranged. But our understanding of how the electrons are arranged matches up perfectly with the shape of the periodic table. These blue columns here represent the s electrons. The s subshell can hold 2 electrons, and there are 2 columns here. Over here, is that pink? Yeah, pink. The colors on my computer are very different than what's on the screen. These pink ones, how many columns? 6. And how many electrons can the p subshell hold? 6. How many electrons can the d subshell hold? 10. There are 10 columns across here. The F block, which we've talked very little about, can hold 14, and there are 14 across here. So we can actually use the periodic table as a map and just pick out the last term in any of the elements' electron configurations. So let's look at arsenic. So here's arsenic, and if I want to look at, that's not what I meant to do. If I want to look at its electron configuration, there's arsenic. I'm going to look at what period is it in. It's in period 4. This corresponds to 4s2, and this would be 4p, and we're over 3, and so this will end in 4p3. It's in group 5a. It has 5 valence electrons. Magnesium. Magnesium is in the 3rd row, the 3rd period. And it's in the S block, so its last term is 3s, and it's in the 2nd column over, it's 3s2. How about radon? Oops, that's radon down here. It's in row 6 in the P block, and it's in the 6th column over. Radon ends with 6p6. The D block elements are a little bit funny because of that whole orbital splitting thing. So here we go, 4s1, 4s2, and then it's 3d. So I imagine in my chemistry land that this block of elements was originally up here, which would kind of make more sense. And you're kind of going down the stairs, you go down 1 step instead of going down 2 steps. That's a big step. They were up here and they sank. So this is the 3rd level. These are the 3Ds. They sank down, and 4D and 5D and 6D. So the number for the D orbitals is the period -1. The number for the F orbitals is the period -2, but we don't have to worry about those guys. So the number of valence electrons for any main group element except for helium is equal to the group number of its columns. And that's using the American group numbers, 1A, 2A, 3A, etc. The row number on the periodic table gives us the number of the highest principal shell. So germanium in group 4A, 4 valence electrons. Those valence electrons are in the 4th energy shell, 4th energy level. You see how that works? It's kind of like a map, and you just need to pick things off the grid. The transition series, those elements, these guys down here, those represent the filling of core orbitals. And so the number of valence electrons for them is pretty much constant. Most of them have 2 valence electrons. There are a couple of exceptions. Let's look at those. Chromium and copper. So as we're going along here, 4s1, 4s2, there's 4s2 with 3d1, 3d2, 3d3. We expect this one to be 3d4, just adding one more electron. Each box we go across, we're adding one more electron, and it seems to be going into the 3d subshell. But we get to this one, and it's funky. What happened here? This is 4s1, 3d5. Well, it turns out there is, it's lower in energy for chromium if it has a half-filled 4s orbital and a half-filled 3d subshell. All the orbitals in that 3d subshell with 5 electrons are going to be half full. Let me draw that for you. So if it's 4s, and then next up we have 5d. So 4s2, 1, 2, 3, 4. That's what we expect for chromium. But that's not what happens. So if we think about that hostel for the, I've switched it now because I like your idea, from a hotel for grown-ups, it's now a hostel for Boy Scouts. I can do that because it's my analogy. It's a little bit like there's some weird deal at the hostel that if this room and this room are half full, you get some kind of a discount. And so the Boy Scout over here says, well, hey, I move up here, I get my own bed, and we all get a discount? Why not? That'd be great. Now the question is, can I erase that arrow without screwing up everything else? Probably not, but we'll try. So he's going to move up there. And that's going to be a bonus situation. So that's what happens with chromium. Then with manganese, we're adding one more electron. Now it's better to put that electron in that 4s. And so we get that electron back. And then we keep going on. And we add another one for iron and for cobalt and for nickel. And then we get to copper. There's something that's wrong. No? 2, 4, 6, 8, 10. I don't know. I'm seeing things. We get to copper. That's right. We need to add an electron. So we add one in here. And that's what we expect for copper. We expect it to be 4s2, 3d9. But again, there's a weird deal. And so this 4s electron moves up here. Now what we have is a completely full 3d subshell and a half full 4s subshell. Things that are completely full or half full are slightly lower in energy than ones that are not. And the electrons in these atoms are all about going to the lowest energy state, finding the lowest energy place. So that's what happens with copper. And then for zinc, one more electron is added and it goes in here. So there are some funny things that happen with these d electrons, with the transition metals. And you'll see that happens again down here with molybdenum and with silver. You see this same kind of a pattern going on. And so you need to remember about chromium and copper, that they do this kind of funky thing with their d electrons. If you're just trying to get through the class and pass the class or even get a B, you could probably blow this off, this exception thing. If you're an A student, you should pay attention to that and remember that. So we can use the periodic table to write the electron configuration for an element based on its position. And so we don't really have to remember that funny chart with drawing all the lines through it, because we can find that on the periodic table. So if we're going to do phosphorus, locate phosphorus, and here is 1s, and this guy is hiding over here because helium and hydrogen are squirrely. So that first row just has 1s2, and then next up is 2s2. And then over here we have p all the way here to 6. This is 2p6. That 3 is talking about this row down here. This is 2p6. And then we come to this part over here. That's 3s2. And we go over here. This is 3p. 1, 2, 3. 3p3. And that's the electron configuration for phosphorus. If we want to use the noble gas configuration, we can put neon. That's not a very good N. It looks like a W. We can put neon. And what comes after neon? 3s2, 3p3. Isn't that easier than the chart? If you see the pattern, it is. If you don't see the pattern, it's all just a big old mess. Let's do gallium. I'm going to erase these guys. So gallium is down here. Right down here in that box. So if we have to write the electron configuration for gallium, we're going to read it off the periodic table. 1s2. Next is 2s2. This is the second row, the P block, and that one's full. 2p6. Then we get to 3s2. You seeing how this works? 3p, we'll go all the way over there to 6, 3p6. Okay, let's get rid of that. Three p6, and then 4s2. Then what's next? What's this group? It's 3d, because it sank down. It's not 4d, it's 3d. And that's all full. That's 3d10. And then 1 into the p block. That's 4 again. That's 4p1. Electron configurations. Any questions? So when we're doing that, it's kind of a recap. You can represent the inner configuration with the symbol for the previous noble gas in brackets. And then the outer electrons are the electrons that come after that noble gas. And you're going to determine those from the position in the particular block, S, P, D, or F. The highest principal quantum number equals the row number. And the principal quantum number of the outermost d electrons is the row number -1. It's like those sank down. So let's do tin. Well, first we have to find tin, and in order to find tin, we have to know what its symbol is. What's the symbol for tin? SN. Did you know that there's tin in your toothpaste? Doesn't sound real appetizing, does it? They don't call it tin fluoride, they call it stannous fluoride. Because people don't know what that is. Because, you know, like a tin can, bleh. But stannous fluoride is a good way to get fluoride to help your teeth be stronger. So if we're doing this, what's the previous noble gas? We're going to go up one row to the end. It's krypton. So this is going to be krypton. And then what comes after krypton? Well, this is 5s2. And then what are all these guys? They're D, but they're one less, so it's 4D. And we've got 10 of those. If you forget the number, you can count them. There's 10. And then this is back to 5. This is P group and 2. 5P2. This is one of those things that just needs a little practice. Once you can see it, it'll be fairly easy to remember. Until then, you just need to practice until you can see it. Any questions?